This video will be going over different types of graphing techniques. Alright, and the first graphing technique we're going to talk about is stretching and shrinking. What that means is that if you have some function, say f of x, what happens if you put a number in front of the function or inside the function with the input value? We're going to explore what happens whenever you do both of these, okay? And we're going to use the absolute value function as an example. For instance, part A illustrates what happens when you put a number in front. Likewise for part B. Part C illustrates what happens whenever you multiply the input by a certain value. So now we're going to graph g of x equals 2 times the absolute value of x. Alright, so we're going to figure out what happens whenever we plug in various values of x. Like when x is negative 2, and you plug it into the parent function absolute value of x, you just get positive 2. But remember, g of x is equal to 2 times the absolute value of x for part A. So if you plug in negative 2 into g of x, you have 2 times the absolute value of negative 2. That would be 2 times positive 2, which is 4. Likewise, if you plug in negative 1, plug it into the parent function, you just get positive 1. But if you plug it into g of x, you have to take whatever you get from the absolute value and multiply it by 2, so you'd be 2 again. If you plug in 0, it's 0 for both of those. Plug in positive 1 into the absolute value, you get 1, and then 2 again. Plug in 2 into the parent function, you get 2, then you get positive 4. So if you plot these on the graph, both the f of x equals absolute value of x and g of x equals 2 times the absolute value, you should get the following graph. Okay, here's the graph, and if you notice for g of x, since we multiplied it by a positive 2, it made the graph narrower. It kind of, I guess, stretched it out, if you will, along the y-axis. It stretched it in a vertical direction and made it narrower. So when the number in front for some number times function of x, when you're just multiplying the function by a number out in front, like for g of x, when a is greater than 1, we call it a vertical stretch. Now, for part B, we're going to see what happens when the number is less than 1. Right. Like in part B, our a, if you will, is 1/2. So we're going to do what we did in part A and plug in various values for x. Alright, so here's a table. When you plug in negative 2 into our parent function absolute value of x, you just get 2. But whenever you plug into h of x, whatever you get after you plug it into the absolute value, in this case it'd be positive 2, you have to multiply it by a half. Or just divide it by 2. So half of 2 is 1. Likewise, when you plug in negative 1, you get positive 1 from the parent function, but after you cut it in half, you just get a half. If you notice, it follows the same procedures, or follows the same method. Whatever you get in the parent function, it's always half of that. Like the value for h of x is always half of what you get from the parent function. That's because of the 1/2 in front. So if you plug these points in, negative 2, 2, negative 2, 1, negative 1, 1, and negative 1, 1/2, 1, 1, and then 1, 1/2, and 2, 2, and then 2, 1, you get the following 2 graphs. Right. And here are the graphs for part B. If you notice, since for our y equals some number times f of x. Since our number is a fraction, that means it's between 0 and 1. That's what we call a vertical shrink. When the number in front of our function is less than 1, we call it a vertical shrink. Vertical shrink just makes the graph wider. So now for part C. K of x equals absolute value of 2x. Just so you know, this is going to illustrate what happens when you have some number inside the function, like if you're multiplying the input value. In this case, we're multiplying the input of the absolute value function by 2. Alright, so let's first just show what happens with this particular example. So k of x equals absolute value of 2x. Now there's a property of absolute values saying that when you're multiplying two things inside the absolute value, you can split them into different absolute values. So it'd be absolute value of 2 times absolute value of x. Remember, absolute value of positive 2 is just positive 2. So it's 2 times the absolute value of x, which is the same as g of x in part A. Alright, so this leads me to the topic of horizontal stretches and horizontal shrinking. Basically, for horizontal stretching and horizontal shrinking, remember, this is whenever you have, let me erase this real quick, f of some number times your input. If that number is a fraction between 0 and 1, then we call it a horizontal stretch. And like in part C, if that number is greater than 1, which in part C it was 2, or A was 2, then we would call it a horizontal shrink. If you notice, this had the same effect as part A, which is a vertical stretch. Oftentimes you'll see the same general effect with both of these. Like if it's compressed in the horizontal direction, it will be stretched out in the vertical direction. And if you compress it in the vertical direction, meaning you make it wider in the vertical direction, it will be stretched out along the horizontal axis in the horizontal direction. Alright, the next thing we'll learn about is reflecting a graph. Pretty much whenever you create a mirror image across any line at all. Like for example 2, we're going to use the parent function of just the square root of x. And we're going to see what happens when you put a negative sign both on the outside of the function. We're going to see what happens when you put a negative sign on the outside, and also when you put the negative sign on the with the input. We're going to see what happens when you do both of those. Part A deals with whenever you put the negative on the outside. Like it tells you to graph negative square root of x. You can do what we did in the previous examples and create a table of values. So for part A, if you do a table of values for both the parent function f of x, and then the reflection g of x, we can see what happens. Alright, here's a table of values. We start with 0 because if you plug in any negative number into both the parent function and our reflection g of x, you end up with a negative underneath the radical, underneath the square root. And we can't have negative square roots when we're trying to graph, so we don't even bother with the negative x values. So if you start at 0, you get 0 for both the parent function f of x and g of x. Now, you plug in 1 for the parent function, you get positive 1 for the y value. But if you plug into your transformation, the y value is negative. Likewise, if you plug in 4 into the parent function, you get positive 2 out for the y value. But if you plug it into the reflection g of x, you get negative 2 out. So if you plot these points, you get the following graph. Alright, here are the graphs of f of x in red and g of x in blue. You see how since the y values are negative, it looks like it's just flipped across the x-axis? That's because when you put the negative sign in front, like if you have negative f of x, that's the same as reflecting reflecting just f of x. The negative sign in front just means you're reflecting f of x across the x-axis. That's all this negative sign in front does. Just takes the parent function and just flips it to the other side of the x-axis. Now we're going to see what happens in part B. Part B deals with when you take the whenever you take the inputs and make them negative before you even plug them in, or whenever you just change the sign of the inputs before plugging them in. So again, we're going to create a table of values, and for this example, all the values that we couldn't even plug in to our original function, our parent function, because it would make the parent function negative underneath the square root. You can graph them now, because the negative underneath the square root means it takes the negative x values and it'll make them positive. Likewise, for the original y values that are positive, they would now be negative. Like that positive 1 would be negative 1 and then negative 2, respectively, underneath the radical. That's why they're undefined here. So since now our reflection works for the other side of the x-axis, the negative values, that would create a different set of graphs, a slightly different set of graphs this time. Alright, remember, as usual, the red function is our parent function, in this case just square root of x, and the h of x is square root of negative x. If you notice now, the graphs look like mirror images across the vertical axis, across the y-axis. So, instead of it being reflected across the x-axis, changing the sign on the input before even plugging it into our function just reflects it across the vertical axis instead. So let me put some notes up here to kind of summarize. So to summarize about reflecting across an axis, when you put the negative sign in front, like in the first part, when you put the negative sign in front, that just flips it across the x-axis. It flips it to the other side of the x-axis. And for the second part here, whenever you put the negative sign inside with the input, that just flips it to the other side of the y-axis. And this leads us to the topic of symmetry across an axis. Alright, the first part is similar to reflecting across the y-axis, in which case you plug negative x, plug in negative x into your function. Alright, if negative x equals f of x, it's even. And then for the second part, is similar to reflecting across the x-axis. Meaning, if you take the y values and make them negative, and you still end up with the same function, or an equivalent function, then you can say it's symmetric with respect to the x-axis. For example, here's some examples. For these functions, we're going to test for symmetry with respect to the x-axis and the y-axis. Alright, so for part A, we're going to plug in negative x to test with respect to the y-axis first. So negative x squared plus 4. This is to test with respect to the y-axis first. So if you plug it in, so if you simplify it, negative x squared, that'd be negative x times negative x. Which would just give you positive x squared. So since you got the same thing after plugging in negative x, you can say it's symmetric about the y-axis. So now to test for symmetry about the x-axis. To do that, you have to plug in negative y in for positive y. So you're going to start with negative y equals x squared plus 4. So to solve for this, to get rid of the negative y, get rid of the negative in front of the y. Remember, that's like having a negative 1 in front. So to get rid of it, you have to divide everything by negative 1. So that would give you y equals x squared divided by negative 1 would be negative x squared. And then positive 4 divided by negative 1 would be minus 4. So, since this does not give us the same equation, we know that it's not reflected across the x-axis. It's only reflected across the y-axis. Alright, and we're going to skip the other three, because I think you get the idea of how to test for symmetry now. Alright, and the next thing we're going to learn about is symmetry with respect to the origin. We know it's symmetric. We know a graph is symmetric with respect to the origin is if you change both x to negative x and y to negative y at the same time, and you still get the same equation. I'm going to show you an example of what that looks like. So here's an example. Here's a two-part example. For the interest of time now, we're only going to do part B. We're going to test part B, y equals x to the third, for symmetry about the origin. So remember, if you if you plug in negative y for y and negative x for x at the same time. We're going to simplify it and see if it gives us what we started with. So negative y stays the same, negative y, then negative x to the third. That's the same as negative x times negative x times negative x. Since you have a negative times a negative times a negative, that's the same as negative x to the third. Then you have negative y. So divide everything by negative 1. Then you do end up with what you started with. So yes, by that test, it is symmetric about the origin. And here's a graph so you can know what we mean by symmetric about the origin. Alright, so here's a picture of the graph. As you can see, the pieces of the graph, if you will, are in opposite quadrants. That's what we mean by symmetric about the origin. Whenever they're in opposite quadrants like this, but they look like they're kind of reflected diagonally, if you will. Okay, the next thing we're going to learn about is even and odd functions. A function is even as if you plug in negative x into f and you get the same thing out. A function is odd if you plug in negative x into the function and you get the opposite function out of it. Like for this example, we're going to determine whether each function is even, odd, or neither. For example, part A, f of x equals 8x to the fourth minus 3x squared. You plug in negative x, that'd be 8 times negative x to the fourth minus 3 times negative x squared. Now negative x to the fourth. Remember, that's 8 times negative x times negative x times negative x times negative x. Minus 3 times negative x squared. Remember, that's just negative x times negative x. Now, for the negative x to the fourth, all the negatives would cancel out because a negative times a negative times a negative is a positive, times a third negative is a negative, times a fourth negative would give you a positive again. So that would just give you 8x to the fourth, then minus, remember, you gotta remember the minus after the x to the fourth that we had to begin with. So minus, and then 3 times negative x would be negative 3x, times negative x again would be positive 3x squared. So this gives us the same thing that we started with. When that happens, it is an even function. Alright. Remember, even functions, if you were to graph this, it would be symmetric about the y-axis, if you were to pull up the graph. Now for part B, f of x equals 6x to the third minus 9x. Remember, if you plug in negative x, that's supposed to be 6x to the third. So now if you plug in negative x, that'd be negative x to the third minus 9 times negative x. So now this simplifies to Now the negative x to the third in parentheses would be negative x times negative x times negative x. Multiply that by 6, and that would give you negative 6x to the third. Then negative 9 times negative x would be plus 9x. Now if you notice, if we were to factor out a negative, that negative 6x to the third would be positive 6x to the third. And that positive 9x would be minus 9x. So now if you notice, we have the same function that we started with, just with the negative sign in front. So that means this would be odd. And if you were to graph this, remember, it would be symmetric about the origin. So the last topic we're going to talk about is the topic of translations. Pretty much a translation is whenever you shift a graph horizontally or vertically on the plane. Like for the next example, it says graph absolute value of x minus 4. With the minus 4 on the outside of the absolute value. Whenever it's on the outside like this, that's when you can tell it's going to be a vertical shift, meaning it's going to be shifted up or down. To figure out which direction it goes, let's create a table of values. Alright, here's our table. Like, pretty much for any point you plug in, like say if you're plugging in negative 4, you just get the positive out of it after you plug it into the parent function, like positive 4. But when you plug it into the vertical translation, since it's minus 4, the y value would be 4 less. So the point on the translation would be 4 units below the point on the parent function. Alright. Likewise, when you plug in negative 1, you'd get positive 1 for the parent function. But that point on the vertical translation, since it's minus 4, it'd be shifted 4 units down. So 4 units below positive 1 on the y-axis would be negative 3. Likewise, for 0, the y value for the parent function is 0, but since we're subtracting 4, the corresponding y value would be negative 4. And you can see that for the other two x values on our table as well. So if we were to graph that, it would look like this, with the parent function in red and the translation in blue. You notice the minus 4 just shifts it's just shifted down 4 units. Alright, here's the point 1, 1. For instance, that we noticed was on the original function, on the parent function. The corresponding point is just 4 units below at the point 1, negative 3. And likewise, it's 0, 0 for the parent function. It's now at 0, 4 for the translation, or 0, negative 4. So as you can see, it's just shifted downwards 4 units. So to summarize for vertical translations. Alright, so whenever you have f of x, some function, plus a number on the end, that's translated upward. It's translated upward c units. Like if we had plus 4 on the end, it would have been shifted upward 4 units. Likewise, if you have some function minus a number, like minus c, it would be shifted downward c units. Like since we had minus 4, that means it was just shifted downward 4 units. Now we're going to look at an example of shifting a graph horizontally. Alright, for this example, you see how we're subtracting, in this case subtracting from inside the function. We're just subtracting directly from the input before we do anything else. This would be a horizontal translation, meaning it's shifted left or right. Now also, a lot of people just assume that since we're subtracting the input, we would shift to the left, since that's the negative x direction. But let's check our table of values before we say that, just to make sure. So here's our table of values. If you plug in negative 2, it looks like, well, for a parent function you just get positive 2. But for the horizontal translation you get positive 6. Likewise, if you plug in 0 into our parent function, you'd get 0, but for our horizontal translation you'd get positive 4. Since it's shifting in the positive, since the x values, at least for those two, are increasing by 4, it looks like we may be shifting in the positive x direction, which would be to the right. But let's go ahead and check our graphs to make sure, because if you look at the corresponding y values for when x is 2, 4, and 6, it doesn't appear that way. So let's go ahead and graph it to see. So here's a picture of the graph with our parent function in red and the translation in blue. So, if you notice, it looks like the blue translation was just shifted right 4 units. And basically, to tell horizontal translation, I'd recommend just looking at the vertex when possible. You can see right here the horizontal, like for the vertex of this graph, you can tell it's shifted to the right 4 units, so that tells you that the graph was shifted to the right as a whole. And this leads us into what we're going to talk about next, which is, in general, what happens when you subtract something from the x. When you're subtracting from inside the parentheses or inside the absolute value or whatever, that actually means you shift right c units. And whenever you're adding to the x inside the parentheses or inside the absolute value or whatever, that actually means that you're going to the left c units. Now for one last example, where we do more than one translation at the same time. Now we're going to do part A and we might do part B as well. Part A we're doing, well, part A and B we're doing with the absolute value function. This +1 on the end, let's figure out what the translations are that we're doing. This +1 on the end means that we're going up 1 unit. If we're adding 3, that means we shift the graph to the left 3 units. Then the minus sign on the front means that it's reflected or flipped across the x-axis. So, if we go ahead and graph this function f of x, it should look like this. Notice, remember the vertex starts at 0, 0, so as you can see it shifted to the left 3 units, the +1 shifted it up 1, and now it's flipped. It's gone from facing upward to facing downward. So now on to part B. H of x equals absolute value of 2x minus 4. Now you could say that it looks first that it's shifted to the right 4 units, but the 2 in front of the x is kind of throwing us off. It's kind of hard to figure out whether that'd be a vertical stretch or whatever. So, you could say that it shifted to the right 4 units and then it'd be a horizontal shrink. Or, if you don't like having this in front, the 2 in front of the x, what you can do, since 2 and 4 are both divisible by 2, you can factor a 2 out and you're left with x minus 2. Now, since we're multiplying, you can split them into different absolute values. So absolute value of 2 times absolute value of x minus 2. Now, the absolute value of 2 is just 2, so it's equal to 2 times the absolute value of x minus 2. So now it looks like the other examples we've done where there's no number in front of the x. So now, we know that the absolute value function, we can also say that it was shifted to the right 2 units and also stretched by a factor of 2. Stretched vertically. So if you were to graph that now, it would look like, notice here the graphs, if you notice from the original function in red to the translation or transformation, you notice the vertex is shifted to the right 2, which is where the minus 2 comes from. And it's just made narrower, which would be a vertical stretch. It would also be a horizontal shrink. So, either way you would have said it, it would have been okay. I like this way better, though. Because I like if we can get rid of the number in front of the x, if possible.